Okay, let's continue for the last bit.
Genau. Als die richtigen Clubs, genau, voll. Deswegen war das aber echt nice.
And before I write down further equations, let me now first show you what this means and how it looks. So this, as we discussed, the solution for this whole thing are these things. And one can of course plot them, but then of course one also needs to specify what these different numbers are. And to make things simple, I set this delta B function to 0. Remember that this delta B function is part of the magnetic field, so it's the magnetic field has only a component in the z direction. It has the strong B0 field, and it has a space and time varying component. So I think we correctly have to call it the B2 field, because B1 is the excitation pulse, which we don't discuss, but this is how things are manipulated during data acquisition and slightly before data acquisition. So that's the delta B, and of course one can set this to 0, and if it's set to 0, then of course one only has this gamma B 0. Now this thing is then fairly straightforward to implement. So this is the implementation, so that's the MATLAB code that you can look at, and I'm now showing you. So of course the whole thing is a function of time, so I define some time interval with some temporal resolution and create then a vector over time, and this has a certain dt. Of course, if you want to do simulations, you have to specify parameters, and I'm specifying here a t2 time constant. Again, we're looking at a single location, so our r is fixed, so we don't have a function of space but just a value, t2 being 1 and t1 being 3. Remember also from the Hüttel business that t1 is the recovery along the longitudinal axis, so meaning that it's also relatively slow, so it has a longer time constant, sorry, t1 has a longer time constant than t2, which is also why this t1, t2 nomenclature is a little bit weird in this order. Anyway, the omega 0 is just the product of the gyromagnetic ratio, which depends on the nucleus that you use. We assume we use whatever, so let's say protons, and multiplied with the strength of the magnetic field, which we also assume is whatever. So we assume omega 0 to be 10 in this case. And we assume an initial condition corresponding to this. Actually, the initial condition business is fairly tricky if one looks in even more detail, but I don't think I want to. So what the exact values are, because this is after excitation. Thing is, if one wants to look at the solution, what these equations mean is just that you that you can compute for each time point the value of the x component, the value of the y component, and the value of the z component. Yeah, so x, y, and z. And the solutions that we wrote down just have this form, so there's an exponential decay, and it's multiplied with this omega cosine sine omega business, which, if you are familiar with rotation matrices, which you find in the Nishimura, you can also understand as rotation matrices being applied to two-dimensional vectors. Otherwise, you just appreciate that if you do this, you get a rotation. So this holds for M1 and M2, for also Mx and My. For Mz, we just have an exponential decay. Yeah, so we didn't discuss that in the last hour. We talked briefly about that the time before. It's just the differential equation for Mz just specifies an exponential decay. That's the analytical solution, and this you can just compute by cycling over the t values. What I also do here is to compute a numerical solution using Euler integration. So remember that we discussed Euler integration before Christmas. which essentially works by evaluating the derivative and then always at a specific for a specific value of the magnetic moment vector, and then adding the derivative and a small multiplied by a small amount of time. Yeah, so that's the Euler integration for something a little bit more complex than before Christmas, namely for our system, which needs to, of course, evaluate the derivative. And for this, of course, there's another function, subfunction down here, which evaluates the evolution function of the magnetization dynamics for our delta B being 0. So this has these equations here. So my times omega 0 minus 1 over T2 times m1. So that's the x, y, and z components according to the differential equations after solving the cross product. So that's this, but for delta B being 0. Yeah. So this again. So if you think currently things getting a little bit out of hand in terms of complexity, really go over the stuff that we went over before Christmas, and then see the parallels to what we're doing now. Because the only thing that has changed is that the expressions that we put in, or that are part of the differential equation and of the numerical integration in this case, are a little bit more complex, but the logic is exactly the same. Yeah. So it's the general stuff is not more complex. It's just that the specific expressions are a little bit longer. And then you can also always think that, oh, it's the same thing as this, but a little bit more complex. And then you're happy and can go partying, whatever people do, I don't know. Now, if one plots this is what happens. So we're starting here with at x being 1, y being 0, and z being actually minus 1. And then the blue line is the numerical solution, and the blue line is the analytical solution, and the red line is the numerical solution. Somehow it doesn't want to print it right now. So we're starting here, and then this is an evolution over time, right? So as time progresses, we do this kind of movement. So it's of course easier, looks a little bit like a Christmas tree if you want. It's a little bit easier to think about if it moves, but it's a 3D thing, and it doesn't help in a way to not appreciate that it's a 3D thing, because the good thing about 3D things is that you can still imagine what these are. The gray thing here is just the Z magnetic field, which is here, of course, it doesn't change. It's on a given location. And what I also plot here in the xy plane is just the x and y component of this magnetic moment vector. Any ideas why I plot the x and y here separately? So which then looks a little bit like, wow, nice, psychedelics. Any idea why I'm focusing here also on this x and y business? Like this. Do you remember from the other course, maybe? From the Hütte course? Which is the same course, actually. I want to...
Wasn't it like the T2 that's in its XY plane is one function imaging than the T1?
That's one thing, yes, but there's a more fundamental thing also. Now it's a little bit weird. Let's run this again. So the more fundamental thing that motivates looking at the XY plane in detail, which we will also then next time have to look even more, because we have to re-express our sine and cosine in exponential form to link it to the Fourier business. The more fundamental thing is that the scanners are built in a way that they are only sensitive to signal in the XY plane. So the scanner only measures the signal that is in the XY plane. So whatever the scanner measures at a given time point is this two-dimensional entity that is in the XY plane. And we will talk more about that next time. So the logic that we will follow is that there is some excitation of some Z plane. So we already know where we are in the Z direction, and then we look at the magnetic moment dynamics in this plane that we have excited, and specifically then what's happening there in the XY plane, because that's what the scanner measures. Before we do that, however, I want to today, for the rest, because that's also quick, talk briefly about the gradients. But again, so the whole stuff that we did up to now describes the following dynamics. After excitation, when things are in the XY plane, the magnetization dynamics does the spiraling. It orients itself again with the Z direction. Remember, this is a fundamental thing about MR, that at equilibrium there's this orientation about the Z dynamics. There is decay. So the exponential decay in the for the Z component, this refers to that the Z component builds up again. Yeah, so it's 0 here, because here Z is 0 and X and Y, so Y is also 0, but X is 1. And here Z is large again, so it has increased from negative values to less negative values. And in the XY, there is the spiraling movement and decay. Yeah. One thing I couldn't really say what is weird about this last time. One thing that is, for example, weird about this, if you think in terms of the very basic spin thing, is that you have to think about this decay in the XY plane in terms of a phase decay. So remember when we talked very early on about the spins precess in this field and they don't decay, right? They just precess. But the summed magnetization after some time, because everything gets out of phase, this decays. So if you are interested more in how you get from the spin nuclear dynamics to this net magnetization dynamics that we now always look at, there's some stuff in this other paper by this Italian guy, this Sebastiani or so, that's also on in the Google Drive, so you can have a look at that. But so this is why I'm trying to stress that we are not talking about the spin nuclear dynamics here, but at this net magnetization dynamics. And it's even easier if you just think, okay, this is the model. This is essentially what you observe if you measure with the MR scanner, and what happens on this micro quantum level, I just don't care about, because I'm dealing with the signal here. So now, before we are done for today, I want to, if there are no questions about this at the moment, briefly introduce linear gradients, because we will need them for the rest, because they will help us, or they essentially enable the imaging process. Let's see, okay, that should work. So this leads us back to our magnetic field. So our magnetic field, as we discussed last time, is a function in general of both space and time, and allocates to each location in space and time a value which only has a non-zero aspect along the Z direction, but this value along the Z direction can vary with space and time. So it has contributions from the static magnetic field and from what we always say, from the gradients that are turned on during the imaging process. So we're not talking about excitation, but the gradients that are turned on during excitation. Now the question is, what about this function in more detail? So what's actually going on with that? So remember, we have now solutions where we also are interested in the integrals of this function over time, so the temporal integral of this function, so the temporal integral of the gradient function. So if we want to calculate things more explicitly, when we not set, like I just did, just set this to 0, it makes sense to be a little more explicit about what this delta b function actually is. And the function that we are specifically interested in takes for the delta BRT the following form. So if we talk just about the delta B function, this, of course we can define whatever we want, but as long as we can somehow implement this on an MR scanner. But the one that is typically used and that also helps us to understand imaging is that we use a linear gradient function, which look, something's slightly, no, that's fine, yeah, there was something was wrong. So remember that this yields something in R3, and this just yields a real value because this is just what's going into the Z component. So this function is usually defined as this. And the question is, of course, then what this GT is. And this is what I will now call the gradient function. Which is a function that is a function of time only. And looks like that. So there is so the idea is that there are linear, and this linear gradient I will explain in a second, there are linear gradients that can change over time. Okay. There are functions, so there is something that we can call the x gradient, the y gradient, and the z gradient, and we can say we turn on the x gradient at this time, or we set it to 0. Yeah, so we can say gx of t is 1 for a certain time, and then it's 0 again. Now, in which sense is this linear? Well, I mean, if we look at what we actually just defined here, so what this means, if you look at it in a little bit more detail, is that our BZ has the explicit form B0, and then we have to compute this dot product between our gradient function and our odds vector, so our location vector. So if we do that, gx, gy, gz, transpose it and multiply it by r. Remember that r is x, y, z. Then we of course get gx tx plus gy ty plus gz tz. This is a little bit weird here. What is this? Gy. So what this means is, this is fairly simple, but maybe looks a little bit unfamiliar. So if you look into the z axis only, so if this is x, so this is space x, and you compute the magnetic field in terms of the x direction, so let's call this bx, you have some constant that you have some value that you multiply with x. If we now assume that this gradient function is constant over time, so that it doesn't change with time. So we just have gx, for example, and this we define as 2. Then we just have the function 2 times x. So we have this kind of outcome or whatever. This is our gx times x. Yeah. So this gx, so these values here, gx, gy, gz, they are the slope, if you want, if they are turned on all the time. They induce a linear affine, if you only look at the gx, gy, actually a linear, not only a linear affine, variation with space. Meaning that at this location in space here, the magnetic field is larger compared to this location field, this location in space. Yeah? Here, high magnetic field, here, low magnetic field. This now extends in the x, y, and z direction potentially, and so this slope parameter of this function can be turned on and turned off. So this will be important for the imaging process, so that sometimes you induce this variation over space in this linear sense, and sometimes you don't. Finally, with respect to maybe the notion of gradients, so if one computes the gradient vector of the z component of the magnetic field, so that would mean the partial derivatives with respect to x, y, and z. Then this is fairly simple. So you compute the derivative with respect to x of bz, with respect to y of bz, and with respect to z of bz. This is, of course, then just the derivative of this function with respect to x, with respect to y, or with respect to z. So what's the derivative of this function with respect to x, where the only dependence on x is actually here? Gxt, exactly. And the same logic then applies to the other ones. So the reason why I'm writing this out is just to give some additional, or maybe just give some meaning to the notion of gradient here. So the gradient of the magnetic field is, like any gradient, is the vector of the partial derivatives in all directions, and the gradient vector of if one uses this setup of a linear gradients, is then just the gradient function. Yeah. So the thing is, what this does, it might look more complex again, but actually it makes things simpler, because we now have an explicit definition of our delta BRT function. So this is not now only delta BRT, and it can be anything. So we can, for example, in the x, y, or z direction, add the square with respect to x, or add, I don't know, pi or whatever. So it's now clear what we want to use for our delta B function. Namely, we want to use a linear dependence on space that we sometimes can turn on. So it's sometimes we can induce something like this, and at other times, when we feel like it, we can say, okay, let's turn this gradient off, which means that there is no variation of the magnetic field over space at other times. Yeah? And this will relate this formulation with the delta B closely to the design of sequences, where you turn on a gradient and then you turn off a gradient, and somehow you use this to create images, and what the participant hears is, well, that's this. We haven't discussed yet, so I'm now just introducing this, because we will need it later, but we haven't, of course, not discussed how this is used. So just keep it in mind for later, that we will use these linear gradient functions. Questions about this?
Yeah, we're just a bit confused by way that should be x at the y-axis of the, where you have the x space on the x-axis, and then we're thinking like and the x on the y-axis. Because we were talking about dz before, so we're just
that's true. Yeah, so that's definitely correct. So that's we should, yeah, you're completely right. So we should call this that's BZ, but we look only, so BZ extends in 3D, right? So in principle, BZ is happening everywhere in space, and we only look at what's happening with BZ in the X domain. Yeah. So of course, yeah, because so it's definitely BZ, but only with respect to X. Yeah, because it's one dimension. It's the one-dimensional projection of this three-dimensional function. But it's a good point. Yeah. Yeah. Other questions? No. Good. So the next thing then that we have to do is, or what we will do is to zoom into the xy plane. So we forget a little bit about the z dynamics and we only consider the xy dynamics next time, and then use these dynamics for which we now have solutions, and our knowledge about complex numbers and Fourier analysis to then link these dynamics to the process of Fourier analysis. So if you haven't done recently, I would really recommend to revise Fourier analysis at this point, specifically also complex numbers and this business that we did long ago in autumn. Yeah, who's still wanting to take this as the oral exam? I'm just interested. So who's taking EG or who's taking MI? You have to decide when you walk into the office, and you have there are two potential dates for the oral exams. One is the week after the term ends, so end of February. The other one's the week before the summer term. As you all know. So who's thinking about still taking oral exam based on this? Good. So the teaching is not too bad. So it's not completely has thrown you off. That's good to know. Good. Then see you this afternoon at the talk, and then next week.